Alright, welcome back. In this second video of trigonometry review, I want to talk about right angle triangles and describe how the three most basic trigonometric functions, sine, cosine, tan, are defined in terms of ratios of side lengths of right angle triangles. So in this triangle on the left-hand side, I have labeled the angle in the bottom left, theta. I've labeled the side opposite that angle, opposite. And I've labeled the hypotenuse, the longest side of the triangle, the one that's opposite 90-degree angle, that little corner. So opposite that corner, I've called it the hypotenuse. And then the other side that's not opposite the angle, not the hypotenuse, I've called it the adjacent. And this is a standard labeling. Keep in mind that the opposite and the adjacent are defined with respect to the reference angle theta. If I was to move theta up here, then my adjacent and my opposite would switch. They'd swap roles. So it's the opposite and the adjacent, those are relative to theta being defined in the bottom left corner. Anyways, based on this picture, the sine function, sine of theta, is defined as opposite or hypotenuse. So you can picture what the output of that function would be for, let's say, a very small angle. What would the sine of 0 look like? For example, if you plug 0 into that function, what comes out? Well, the opposites. I'll draw that. I'll draw what does sine of, or what does an angle of 0 look like? Maybe I'll draw a very small angle. So I'll call this the sine of small. Not a very good picture. It's hard to draw. Oh, I have to do better than that. Okay. Slightly better. So this is the opposite. This is the hypotenuse. This is the adjacent. Now imagine making it smaller. What's going to happen? Well, eventually, the opposite's going to shrink down to nothing. So in terms of your SOHCAHTOA, sine being opposite over hypotenuse, you're going to have 0, because the hypotenuse is going to shrink to nothing, divided by the hypotenuse, which does not shrink to nothing. The hypotenuse stays as whatever its length is as you decrease that angle. And then 0 divided by 10, or 0 divided by 2, or 0 divided by 7, or 0 divided by 1, whatever it is going to be 0. You could also think about what happens when we're taking the sine of something that's close to 90. Sine of almost 90. Or almost pi over 2 in our preferred radian measure. So I'll draw that. I'll do my best. Oh, already not done very good. Done. All right. So this is going to be almost a 90-degree angle inside this corner down here. So what happens here is that the hypotenuse and the opposite, if you were to continue bringing that hypotenuse, that angle closer and closer to 90 degrees, closer and closer to pointing straight up, what's going to happen is that the adjacent is going to shrink down to 0, and the opposite and the hypotenuse are going to scrunch right on top of each other. Oh, I'm going to have to describe that probably a little bit better. So imagine taking this side here and continuing to swing it to the left, pulling it left so it ends up like this. Ends up pointing straight up here, like that. Well, the adjacent side is going to shrink down to 0. And the hypotenuse and the opposite are going to scrunch right on top of each other. So sine of pi over 2, that's opposite over hypotenuse, which is hypotenuse over hypotenuse, if those two sides are going to scrunch on top of each other. And if you have 7 over 7, or 1 over 1, or 2 over 2, or 10 over 10, whatever it is, something over itself is 1. Okay, the next trig function is a cosine. From your SOHCAHTOA acronym, cosine is defined as adjacent over hypotenuse. And we can use the same pictures. So think about what happens to this cosine function when the angle is very small, or when the angle's almost 90 degrees. So for the very small, cos of 0, let's look at our picture again. The opposite shrinks down to nothing when the angle gets very small. But look what happens to the adjacent. So imagine scrunching that angle down even further. The hypotenuse and the adjacent are going to squish right on top of each other. So the cosine of 0, we're going to have adjacent over hypotenuse, which is hypotenuse over hypotenuse, which is 1. But our cosine of pi over 2, the opposite thing is going to happen. Let's go back to the second picture now. So cosine is adjacent over hypotenuse, and in the second picture, as we spring this angle straight up, the adjacent shrinks down to nothing. So 0 over hypotenuse, which is 0. So I'm just going to add some labeling here. Opposite goes to 0, and adjacent goes to hypotenuse as the angle goes to 0. And then for the other triangle, for the almost 90 degrees, the adjacent goes to 0, and the opposite is going to squish onto the hypotenuse. Okay, now the last trig function, there's more trig functions than these three, but the last one for this intro is the tan function. Tan is defined as opposite over adjacent. And we can think about what happens if we plug a small angle into tan. So tan of 0. So we're going back to that first picture now. We're going to have the opposite over the adjacent, and the opposite's going to 0. The adjacent's going to the hypotenuse. So 0 divided by anything is going to be 0. So tan of 0 is 0. And then tan of pi over 2. See what happens there. Opposite over adjacent. This time the opposite goes to the hypotenuse, and the adjacent goes to 0. And here we have a problem. You know you can't divide by 0, so this is going to be undefined. So those are their three core trig functions, sine, cosine, tan, defined in terms of ratios of side lengths, as well as what do these trig functions do if you plug in angles that are 0 or angles that are 90 degrees. I've been mentioning the word function because we're going to be going beyond the description of trigonometry as ratios of side lengths of triangles. We're going to be thinking about the graphs of a function f of x that's equal to the sine of x, f of x is equal to cosine of x, and f of x is equal to tan of x, as well as composite functions involving those trigonometric functions. The relationship between the trigonometric functions and the triangles will always be there. It's always a connection that we can draw on to solve problems. When it comes to doing things with functions, we will talk later about how to take the derivative of trig functions. But before that, and actually needed for that, we're going to need to describe how to evaluate trig functions at more than just 0 and pi over 2, but at other angles, like at pi and pi over 2 and pi over 3 and so on. We're going to restrict ourselves to the evaluation of trigonometric functions at only special angles, only special increments of pi. So I mentioned graphs of the trig functions, and I'll show you later on in a different video how to construct the graph of the sine function, the cosine function, and the tan function. Maybe I'll just do the sine function. How to construct those based on a few simple rules. But, you know, you've probably seen it before, and just to show you what the final result is, if you carefully construct the graph of the sine function in terms of ratios of side lengths of a triangle, keeping in mind positive and negative x and y values, you get this shape, you get this wave. It's a periodic function. So if you did a copy paste, if you took a screen grab, a screen capture of one little block of this function from here to here. So you do a copy paste of that little window there. And then you would, oh, maybe I didn't go far enough. Hold on. I gotta think more. Yeah, that's fine. So you copy paste this, copy that, and then paste it here. And then paste it here. And you'd paste it here. And so on. You keep pasting it. And that's what it means for a function to be periodic. Is that if you could find a segment that you could copy paste and reproduce the entire graph, then the function is periodic with, for the smallest size that you're able to do that for, periodic with that x width, the width of this window being the period. Now it turns out for the sine graph, that function is, its period is 2 pi. For the cosine graph, its period is also 2 pi. For the tan graph, its period is pi. It repeats every pi units. This property is important, but it's not the most important property of trigonometric functions that we'll use inside this course. Once in a while, I'll talk about the period of the function, and this is what it refers to. So I mentioned we're going to be evaluating these trig functions at special angles, and made brief reference to the fact that these are the sine, cosine, tan are the three most basic trigonometric functions, but they're not all of them. We do have 3 more, and there's even more than this. But the next 3 are called the reciprocal trig functions. Secant of x is defined as 1 over the cosine of x, so the reciprocal of cosine. Cosecant, CSC, is defined as 1 over the sine of x. And cotan is defined as 1 over the tan of x. In terms of the special angles that we're going to evaluate all of these functions at, we have 0, pi over 6, pi over 4, pi over 3, and pi over 2 being the special angles that are in what's called the first quadrant, the first 90 degrees of the unit circle. We also have the extended angles. There's lots of these. So an example of an extended angle would be negative 11 pi over 6. When we describe negative angles, we're going to describe traveling around the unit circle in a different direction than positive angles. All of our extended angles are going to be increments of 30 degrees, or pi over 6, increments of 45 degrees, or pi over 4, or increments of pi over 3 degrees, 60. And I'll continue this component in the next video.